So now in this video, we'll be looking at the concept of acceleration due to gravity. So acceleration due to gravity, you can say it is the acceleration with which anything will fall towards Earth if it is free to move. So there is no external force acting on the body. Suppose there is a ball which is allowed to fall to a certain height. Then the acceleration with which it is going to fall towards Earth is called the acceleration due to gravity, represented by small g. So if I consider that m is the mass of this body, then the force acting on this body is equal to mass into acceleration. And if the force is due to gravity, then the acceleration of the body is called the acceleration due to gravity. So we write F is equal to mg. So you can say that the acceleration due to gravity g is equal to force divided by mass. Okay, so if I take mass as 1 unit, then the acceleration due to gravity g will be equal to F. So we can say that acceleration due to gravity is numerically equal to the force which is acting on a unit mass when it is placed on or near the surface of Earth. Okay. So acceleration due to gravity is basically acceleration. It is acceleration with which something is falling towards Earth. On Earth, the value of acceleration, average value is taken as 9.8 meter per second square, which is or approximately we take 10 meter per second square also in case if we want to make our calculations easy. So meter per second square is the unit of acceleration due to gravity, and acceleration due to gravity is a vector quantity. It is a vector quantity. So, and the direction of acceleration due to gravity is always towards the center of Earth. Acceleration due to gravity direction is always towards the center of Earth. Okay. So now we can see the relation between small g and capital G. So let us see the relation. What is the relation between small g and capital G? That means acceleration due to gravity and universal gravitational constant. So suppose we consider Earth as a spherical body. Let O is the center of Earth. Let capital M is the mass of the Earth. And the radius of Earth is taken as capital R. So radius of Earth is taken as the capital R. And suppose there is an object of mass small m, which is placed on the surface of Earth. So it is at a distance capital R from the center of Earth. Okay. So according to Newton's law of gravitation, the gravitational force which is acting between the Earth and this object will be F is equal to G capital M into small m divided by r square. So this is in accordance with Newton's law of gravitation. And the gravitational pull which is acting on this body is equal to m into g, which we also call the weight of the body. So if I equate these two equations, so what I get is we get mg is equal to g into capital M into small m divided by r square. Right? So small m gets cancelled on both the sides. So what we get is we get small g is equal to gm by r square. So this is the relation between small g and capital G. So from this relation, we can easily see that the value of acceleration due to gravity will depend on the mass of the planet on which we are calculating it, and also about on the size of the planet or the radius of the planet. Okay. Now, we also know that density is defined as mass per unit volume. So we know that density is equal to mass per unit volume. And if I take volume of Earth, because Earth is a sphere, so volume can be taken as 4 by 3 pi r cube. 4 by 3 pi r cube. So what I can do is, so I can say that, okay, mass of Earth will be equal to density rho into 4 by 3 pi r cube. Okay. So that means small g can also be written as capital G divided by r square multiplied by mass. So mass I'm putting as rho into 4 by 3 pi r cube, where rho is the density of Earth. So this r square will get cancelled. So we are left with only one r in the numerator. So this implies that small g is equal to 4 by 3 pi g rho r. So this is one more relation which says that, so like according to this relation, small g is equal to gm by r square, I can say that if mass remains constant, then g inversely proportional to r square if capital M constant. But it is not always true, because according to this relation, if density remains constant, if rho is equal to constant, then you can say that acceleration due to gravity g will be directly proportional to the radius of Earth. Okay. Now, see, the acceleration due to gravity is not constant. It varies. It varies with height. It varies with depth. It varies when you go from one place to another place, say like from equator to pole. So we'll be looking at the variation of acceleration due to gravity. So under this heading of the variation of acceleration due to gravity, we can consider the effect of altitude. So number one, we are going to look at the effect of altitude or height. Effect of altitude. Okay. So, so let us consider that, suppose this is the Earth and O is the center of Earth, R is the radius of Earth. Okay. Suppose A is a point on the surface of Earth where the value of acceleration due to gravity is g. And if you go to a certain height h, so above the Earth to another point B, suppose the acceleration due to gravity at that point is taken as g dash. Now we know that on the surface of Earth, the value of acceleration due to gravity small g is given by the formula gm divided by r square. So let us say this is our equation number one. And the value of acceleration due to gravity at a height, suppose g dash, is given by gm divided by r plus h whole square, right? So let's call this as equation number two. So if I divide equation number two with equation number one, equation number two divided by equation number one, so what I will get is, I get g dash divided by g is equal to gm divided by r plus h whole square multiplied by, now g is gm by r square, so r square goes into the numerator, and in the denominator we are left with gm, right? So gm gets cancelled in the numerator as well as denominator. So what we are left with is r square divided by r plus h whole square. R square divided by r plus h whole square. So let's call this as our equation number three. Okay. So now what I will do is, I can write the same equation as g dash divided by g is equal to, so r square as such. And in the denominator, if I take r square outside, what I get is 1 plus h divided by r whole square. Okay. So this r square will get cancelled in the numerator and denominator. So what we have is 1 over 1 plus h by r whole square. Okay. Now I can take this 1 plus h by r whole square into the numerator. So what I'm left with is 1 plus h by r raised to the power minus 2. Raised to the power minus 2. Okay. So now, if the height is, very, very small as compared to radius of Earth, then h by r, will be very small as compared to 1. So we can, expand the right-hand side by using binomial expansion also in this case. So according to binomial expansion, if we have 1 plus something like 1 plus x raised to the power n, where x is very small as compared to 1, can be written as 1 plus nx. So power will come below. Okay. But we are left with 1 plus nx. So what we have is g dash divided by g is equal to 1. So this power minus 2 will come down. So what we are left with 1 minus 2h divided by r. G dash divided by g is equal to 1 minus 2h divided by r, which implies that g dash will be equal to g into 1 minus 2h divided by r. So this is the value of acceleration due to gravity. So this formula, this is an important equation. Again, I call it equation number 4. So this equation number 4, I'm going to use when the height is very, very small as compared to the radius of Earth. Okay. While equation number 3 can be used to find the value of acceleration due to gravity when the height is comparable to the radius of Earth. Okay. When the height is comparable to the radius of Earth. So, for example, if I'm going to a height which is approximately equal to the radius of Earth. So we have two formulas here for G. One formula is G dash is equal to G into R square divided by R plus H whole square. And another formula for G is variation of G is G dash is equal to G into 1 minus 2H divided by R. So this is another formula. So if height is approximately equal to radius of Earth, and if I use the second formula, what I will get is G dash is equal to G into 1 minus, so if I put H is equal to R, 1 minus 2 R divided by R, so R gets cancelled and 1 minus 2 gives you minus 1. So what we get is G dash is equal to minus G. So this is wrong result because acceleration due to gravity cannot be negative here. So, and if I use equation, the first equation, what we have is G dash is equal to G into R square divided by R plus, or if I put H is equal to R, so R plus R whole square. So this is equal to G into R square divided by R plus R is 2R. 2R squared gives you 2 to the 4R square. So R square will get cancelled. So what we are left with is G by 4. So we have G dash is equal to G by 4. So this is the correct result. So we have to just remember that we have to use the variation, this equation number 1 when the height is comparable to radius of Earth, equal to radius of Earth 2 times, 3 times. While if the height is very small, if we are going 700, 800, 2000 kilometers above the surface of Earth. So we'll use this equation number 2. Okay. And if I just try to analyze in detail to do some more analysis of this equation number 2, so what I will get is, okay, let me just go to the next page. So we have written this equation that we have G dash is equal to G into 1 minus 2H divided by R. Okay. If I expand this equation, so what we have is G dash is equal to G minus 2H G by, okay. So this equation can be written as G minus G dash is equal to 2H G by R. So this is the expression which is giving me the decrease in the value of G with height is equal to 2H G by R, right? And if you want to find the fractional decrease, what is the fractional decrease in the value of G? Fractional decrease in the value of G will be equal to G minus G dash divided by G. So that will be equal to 2H divided by R. So that will be equal to 2H divided by R. Okay. And if you want to find what is the percentage decrease in the value of G. What is the percentage decrease in the value of G? So percentage decrease will be equal to just G minus G dash divided by G into 100. So that means 2H by R into 100 will give you the percentage decrease in the value of G. Okay. Similarly, acceleration due to gravity also varies with depth. So let us see the effect of depth. So what is the effect of depth? So let us consider, assuming that Earth is a homogeneous sphere, that O is the center and R is the radius. So again, Earth is having some mass, capital M. So capital M here is let us assume that mass of Earth. And suppose A is a point on the surface of Earth. The value of acceleration due to gravity, suppose on the surface of Earth, is taken as small g. Then small g on the surface of Earth is given by the formula small g is equal to g m by r square. So let us say this is our equation number 1. And if I consider that let rho is the uniform density of Earth, if rho is taken as a uniform density of Earth, then we can easily say that the mass of Earth will be equal to volume into density. So volume is 4 by 3 pi r cube multiplied by density, which is rho. So if I put this value in equation number 1, what I will get small g is equal to capital G divided by r square multiplied by mass. And mass is 4 by 3 pi r cube into rho. So this r square will get cancelled with this r. So what we are left with is small g is equal to 4 by 3 pi g rho r. So let's say this is equation number 2. So this relation we have found earlier also. Okay. So we said that if density is kept constant, then small g is directly proportional to y. Suppose you go to some depth d below the surface of Earth. So we have gone to some another point B, which is at a depth d below the surface of Earth. Then that g dash is the acceleration due to gravity at point P. Right? So this g dash, that is acceleration due to gravity at depth d, will be equal to g m dash divided by r minus d whole square. Okay, because this point B, when the body goes to point B, you can assume that it is outside a sphere whose radius can be taken as how much? R minus d. And this sphere is applying the gravitational pull on this object now. So that's why, and here m dash is taken as the mass of this sphere of radius r minus d. M dash is taken as the mass of the sphere of radius r minus d, which is applying gravitational pull on this object. Okay. So we can write this equation as, so like if I put m dash, what is m dash? M dash will be equal to, like m is equal to 4 by 3 pi r cube rho. So m dash can be written as 4 by 3 pi into r minus d cube multiplied by rho. So I can put the value of m dash in this equation. So what I get is, I get g dash is equal to capital G into 4 by 3 pi into r minus d whole cube multiplied by rho divided by r minus d whole square, r minus d whole square. Okay. So r minus d square will get cancelled. So what we are left with is, what we obtain is g dash is equal to capital G into 4 by 3 pi rho into r minus d. So let us say this is our equation number 3. So if I divide this equation number 3 with equation number 2, if I divide these two equations, what I get is g dash divided by g. So that will be equal to 4 by 3 pi capital G into r minus d into rho divided by 4 by 3 pi into g r rho. So this 4 by 3 gets cancelled, pi gets cancelled, g gets cancelled, rho gets cancelled. So what we are left with is, we are left with g dash divided by g is equal to r minus d divided by r. Okay. Or we can write it as 1 minus d by r. That means we have g dash is equal to g into 1 minus d divided by r. So this is the formula which shows the variation of g with depth. Okay. So this is the formula that we have derived. So let us elaborate this formula more. Let's understand this formula. So we have g dash is equal to g into 1 minus d divided by r. This is our formula. So for variation of g with height, we have two formulas. But for depth, we have only one formula. And we can do one special case also over here. Like if we go at the center of Earth, so at the center of Earth, you know that d will be equal to r. So what will be the value of g dash? So g dash will be equal to g into 1 minus. So if I put d is equal to r, what I get is r by r. And r by r is 1. So 1 minus 1 will give you 0. So g dash at the center of Earth will be equal to 0. So you can say that acceleration due to gravity at the center of Earth is 0. That means the weight of the body at the center of Earth will be equal to 0. And this condition is called weightlessness. Because weightlessness does not mean that the mass of the body is 0. Weightlessness means that the acceleration due to gravity at that place is equal to 0. Okay. Now let's do some more analysis of this formula of depth. So as we have written that g dash is equal to g into 1 minus d by r. And if I open this bracket, what I get is g dash is equal to g minus dg by r, right? So if I want to find what is the decrease in the value of g, so that will be equal to g minus g dash. And g minus g dash will be equal to dg by r, right? And if I find what is the fractional decrease in the value of g, fractional decrease will be equal to g minus g dash divided by g is equal to d by r. Similarly, if I find what is the percentage decrease in the value of g, so that will be equal to g minus g dash divided by g into 100. Fractional decrease into 100 means d by r into 100% will give you the percentage decrease in the value of g with depth. Okay. So I hope this is clear to you.